Hey everyone, and welcome. Today we're going to talk about the carbon cycle. It's this enormous, totally invisible system that moves the most basic building block of life all across our planet. You can think of it as Earth's circulatory system, or maybe its breathing system, and it operates on a scale that is just mind-boggling. All right, let's get into it. So I want you to imagine that the entire planet runs on a really strict budget. A carbon budget, right? There are deposits and there are withdrawals. And for millions and millions of years, this budget has been, pretty much balanced. But what happens when you suddenly add a massive new expense that nobody accounted for? Well, that's the big question we're going to unpack here. So first things first, let's look at where all this carbon is actually kept. It's easiest to think of them as the planet's carbon banks, or reservoirs. There are a few really big ones, and you'll see that the amount of carbon they hold, well, it varies a lot. Okay, now this is where things get kind of wild. Just look at the staggering difference in scale here. The overwhelming majority of our planet's carbon, we're talking over 100 million gigatons, is locked away deep in sedimentary rocks. Now compare that to the oceans, and then look at that tiny little sliver for the atmosphere. It's just 880 gigatons. It's a tiny, tiny fraction of the total, but that one atmospheric bank account, that's what sets the thermostat for the whole planet. The oceans are the second biggest player and a much more active bank, holding a truly massive 38,000 gigatons. And of course, there are other important accounts too. You've got the world's soils holding about 2,500 gigatons. And get this, all the plant life on Earth, every single tree, every flower, every blade of grass, holds about 550 gigatons all put together. All right, so we've got these giant carbon banks, but carbon doesn't just sit still, right? It is constantly on the move. We call these movements fluxes, and they basically happen at two totally different speeds. And you've got to understand these two speeds to really get the whole system. First, you've got the fast cycle. This is the biological one. This is the planet breathing, operating over days, months, and decades. We're talking photosynthesis and respiration. Then you've got the slow cycle. This is the deep geological heartbeat of the Earth, with stuff like rocks forming on the ocean floor or volcanoes erupting, processes that unfold over millions of years. And this just shows you the incredible volume of that fast cycle. Every single year, plants pull about 120 gigatons of carbon out of the air. And then, through respiration and decomposition, they release pretty much that same amount right back. The oceans and the atmosphere, they're trading about 90 gigatons back and forth, too. It's this huge, beautifully balanced dance. So, with all this carbon flying around constantly, how in the world does the system stay stable? Well, it does that using something called feedback mechanisms. You can think of them as the planet's own internal checks and balances. Okay, so first you have positive feedback loops. Now, it's super important to know that positive here does not mean good. It just means it amplifies whatever change is happening. It's a vicious cycle. For example, as the planet warms up, ancient permafrost starts to thaw, and that releases methane, a really potent greenhouse gas. That methane then causes more warming, which, you guessed it, thaws more permafrost. The system just keeps pushing itself further and further away from where it started. But on the flip side, you have negative feedback loops, and these are the ones that are stabilizing. They work to pull the system back towards balance. So, for instance, a jump in atmospheric CO2 can actually act like fertilizer for plants, making them grow faster and bigger. And more plants mean more photosynthesis, which means more CO2 gets pulled out of the atmosphere. It's like a natural course correction. For millennia, these fast and slow cycles, along with all those feedback loops, have kept the Earth's climate in a pretty stable place. But in just the last couple of centuries, a brand new and incredibly powerful force has basically thrown a giant wrench into the whole system. And that new flux? Well, it's us. Since the Industrial Revolution, we've been taking carbon that was supposed to be locked away for good in that slow geological cycle, in the form of coal, oil, and gas, and we've been pumping it directly into the fast cycle, straight into the atmosphere. We've basically been short-circuiting a natural process that should take millions of years. So here's the absolute bottom line. We are adding a net 10 gigatons of extra carbon to the atmosphere every single year. Now remember those huge natural exchanges, the 120 and 90 gigatons? Those were balanced. They went both ways. This 10 gigatons is a one-way street. It's extra money being dumped into the budget, and the system has no idea how to spend it. And as you'd expect, the consequences of knocking things out of balance like this are pretty profound. This extra carbon strengthens the greenhouse effect, which traps more heat. And while the planet's natural sinks, the oceans, the forests, are working overtime. They're absorbing all they can,
but they just can't keep up with the sheer pace of our emissions. So more and more of that excess carbon is just left hanging out in the atmosphere, tipping the planet's entire energy budget off kilter.
Look, the carbon cycle is this ancient, incredibly powerful, and complex system that's kept our planet habitable for eons. By shoving this massive new flux into it, we're forcing the system to try and find a new point of equilibrium. And the critical question that leaves us with is this: what will that new balance actually look like? And how is it going to change the world that we all depend on?